What is this? Why is there a math problem in the forest?
It seems we must solve this problem to escape the forest. It is asking, what number is equal to its own square? In other words, when x is squared, it becomes itself. So we just need to find such values of x.
That's easy. For example, if we square 0, it becomes 0 again. And if we square 1, it becomes 1 again.
That's true. This problem feels too easy. There must be some kind of trap.
Really?
By the way, do you think there are any other solutions?
It doesn't seem like there are any others.
Well, normally we would say there are none. Let me show you why. First we move x to the left-hand side. Then let's factor the left-hand side. In this case, we can factor out x. When the product of x and x minus 1 equals 0, then either one of them must be 0. Therefore, the solutions of this equation are only 0 and 1.
Oh yeah, that's how you do it. Alright, that solves it.
Zundamon, watch out! There's another problem coming.
What? It's not over yet? Whoa, this is... Wait, isn't this the same problem as before?
Look carefully, Zundamon. There seems to be a condition on x.
I see. X is neither 0 nor 1. Huh? What does that mean? Weren't 0 and 1 the solutions to the equation?
We've gotten ourselves into a troublesome situation. Let's organize the situation.
Thanks for always organizing things for me.
First, let me note the equation at the top right. The solutions should have been 0 and 1. Both 0 and 1 return to themselves when squared. But now, we must find solutions other than these.
Is that even possible? We just showed that there are no other solutions.
Well, don't panic. Let's look beyond 0 and 1 for now.
Beyond 0 and 1? You mean 2? When we square 2, we get 4. Sadly, 2 doesn't return to itself when squared, so it's not a solution.
Don't give up. Let's keep going. 3 squared is 9. 4 squared is 16. And continuing this up to 9 gives us this.
Okay. As expected, no number except 0 and 1 returns to itself when squared.
That's true in ordinary thinking. So we need to change our perspective. First, let's focus on the last digit.
That's an unusual idea. Let me see.
Did you notice anything?
If we look only at the last digit, 5 squared ends with 5, and 6 squared ends with 6.
Excellent. Right, 5 and 6 don't return to themselves completely, but their squares end in the same digit. Of course, these still aren't actual solutions. So let's take another step forward.
What are you thinking?
5 squared is 25. Here, note that the tens digit is 0. Now change the tens digit to 1. Then 15 squared is 225. Likewise, if we change the tens digit to 2, 25 squared is 625. We'll continue this up to 95 squared.
Wait a minute. I'm starting to see what you're trying to do. Earlier we looked at the last digit, so now we're looking at the last 2 digits.
Seems you figured it out. Yes, let's focus on the last 2 digits. Then we see that only 25 keeps its last 2 digits when squared, meaning its original digits stay the same. So far we looked at numbers ending in 5, but we can do the same for numbers ending in 6. Then we find that only 76 keeps its original digits when squared. This gets us one step closer to the answer.
Does it? But the problem asks for numbers that fully return to themselves when squared. If we only look at the original digits like this, I feel like we won't reach the answer.
That's understandable, but let's keep going anyway.
I think we've reached the point of no return.
So far we've learned that the numbers 25 and 76 keep their original digits when squared. Now, just like before, if we add one digit to 25, only 625 keeps its original digits when squared. Likewise, if we extend 76 by one digit, only 376 keeps its original digits when squared.
After that, we kept on calculating. Then we discovered more and more numbers whose original digits stay the same when squared. One sequence starts with 5 and the other starts with 6. And sometimes we add a leading 0 to show that the number of digits increases by 1 each time.
We've done quite a lot of calculations.
It seems this process can go on forever.
There's no proof, but it does feel that way. Now, if this process really continues forever, what kind of numbers could we obtain?
If we continue forever, the number of digits will increase without limit. So that means we might end up with numbers with infinitely many digits?
It's strange, but an interesting idea. So let's call the numbers obtained by continuing this forever P and Q.
P is the number that starts from 5. And Q is the number that starts from 6.
We haven't actually computed infinitely many digits, so we don't know if such numbers truly exist, or if they would even be uniquely determined. But if such numbers do exist, they would remain unchanged when squared, because with infinitely many digits, their original digits do not change when squared, means none of their digits change at all. So now we've found numbers other than 0 and 1 that stay the same when squared.
I'm not sure if we're allowed to do this, but we at least got something that feels like an answer.
By the way, when you look closely at these two numbers, do you notice anything?
What do you mean?
Then what happens if we add them?
8 plus 1 is 9.
What about these two?
2 plus 7 is also 9.
And these two?
There's more? 9 plus 0 is also 9. Wait, does this mean... every pair of matching digits adds up to 9?
Looks like you figured it out. Yes, for every position, the digits of P and Q add up to 9. Except for the ones digit, where 5 plus 6 is 11.
We calculated P and Q separately, so why do they have this kind of relationship?
So what does this strange phenomenon mean? We can understand it by trying to add the two numbers.
We're adding numbers with infinitely many digits? This makes no sense anymore. But let's try anyway. First, the ones digit. 5 plus 6 gives 11, so we carry 1. Next, the tens digit. 1 plus 2 plus 7 makes 10, so we carry again. Then the hundredths digit. 1 plus 6 plus 3 makes 10 again, and we carry once more.
Here, 2 and 7 make 9. And 6 and 3 make 9. Since every pair of digits adds to 9, the carry continues forever, and the carried 1 disappears into infinity, because all digits above the ones digit end up being 0. Of course, we can't guarantee the calculation truly continues, but it's certainly mysterious.
So that means the sum is 1?
Yes, that's a valid interpretation. Now, the sum of the two infinite digit numbers is 1. So what happens when we multiply them?
Multiplication comes next. Let's do it. This is extremely hard to calculate. It looks like all digits might become 0.
If all digits become 0, the product can be considered 0. This is quite an interesting result. To summarize, the infinite digit numbers P and Q return to themselves when squared. And when added, they become 1. And when multiplied, they become 0. It seems these relations might hold.
Why do such relationships appear? It's mysterious.
Perhaps this can be interpreted as something like VOICEVOX formulas.
VOICEVOX formulas? Please explain.
Very well, let me explain. First, let's review VOICEVOX formulas for quadratic equations. In general, consider ax squared plus bx plus c equals 0, and let its two solutions be alpha and beta. Then these relationships hold between alpha and beta.
I see. Alpha plus beta equals minus b over a. And their product is c over a.
Yes, and this is called VOICEVOX formulas. Now let's think about our equation. This is also a quadratic equation, so if its solutions are alpha and beta, the same kind of relations must hold. I'll skip the intermediate calculations.
Wait, these are exactly like the relations between P and Q. Or, exactly the same?
That's the important point. More precisely, alpha and beta here are the two solutions of x squared equals x. That is, 0 and 1. VOICEVOX formulas tell us that 0 plus 1 equals 1, and 0 times 1 equals 0. In this sense, the relationships between P and Q resembles that of 0 and 1. At least that interpretation is possible.
This is so mysterious. We've obtained 4 solutions to the equation x squared equals x. And the relationships hold not only for 0 and 1, but also for P and Q. Well, if we think that way, it's natural that P and Q add to 1, and multiply to 0.
I'm glad you understand.
Wait, I'm getting sleepy. Now let me explain what's going on behind the scenes. Did today's story make sense to everyone? There are many mysteries left in this story. First of all, do the infinite digit numbers p and q actually exist? Are addition and multiplication of p and q mathematically valid operations? And why does something like Vieta's formulas hold? These questions are actually very deep, so I can't fully explain everything here. So my goal here is to give you a sense of what is happening behind the scenes. First, let's define p and q a bit more carefully. We were calculating numbers whose original digits remain unchanged when squared. Besides the obvious examples 0 and 1, numbers like 625 and 376 also keep their last three digits when squared. There were two sequences of numbers whose original digits stay unchanged when squared. One sequence starts with 5 and the other starts with 6. Let's accept that such sequences exist uniquely and move on. Now, let's call the sequence starting with 5, p sub 0, p sub 1, p sub 2, and so on. And the one starting with 6, q sub 0, q sub 1, q sub 2, and so on. P and q were the numbers obtained by continuing these calculations forever. But p and q are infinite digit numbers, so they are suspicious objects. So let's treat the entire sequence starting from 5 as p. In other words, writing them like infinite digit numbers is just shorthand for sequences. Likewise, we'll treat the sequence starting from 6 as q. P and q look like infinite digit numbers, but in reality they are sequences of finite numbers. That means we can calculate normally with them. For example, to add p and q, we just add their nth terms. Then it looks like this. We add p sub 0 and q sub 0, then p sub 1 and q sub 1, p sub 2 and q sub 2, and this continues infinitely. We would like to call this new sequence the sum p plus q, but we need one more step. Just like when defining p and q, we restrict the 0th term to one digit, the first term to 2 digits, the second term to 3 digits, and so on. Let's call this p plus q. Since every term in the sequence is 1, it makes sense to write it simply as 1. So we get p plus q equals 1. Of course, this doesn't guarantee the calculations will continue the same way forever, but I'll explain that later. Multiplication works similarly, but more digits get ignored. If we look at the lower digits, we see they become 0. Therefore, pq equals 0. Just as before, there's no guarantee the pattern continues. By the way, it might feel like we're conveniently picking out digits to make the calculations work. If that bothers you, think of each digit as gradually getting fixed. For example, in the 0th term, the tens digit is not yet fixed. It becomes 0 at the first term and stays 0 afterwards. Similarly, in the first term, the hundredths digit is not fixed, but it becomes 0 in the second term. In this way, each digit gets fixed to 0 one by one. Now that we're prepared, let's prove the relations between p and q. Well, I'd like to, but the full proof is quite tough, so I'll just go over the outline. I'm going to explain very hard material in a very rough way, so just try to get the feeling of it. One more tool we will use is congruences. For example, the fourth term of p is 90,625. Squaring it indeed leaves the original digits unchanged. We can express this property using a congruence. This means both sides have the same remainder when divided by 100,000. The remainder when 90,625 square is divided by 100,000 is 90,625. And the remainder when 90,625 is divided by 100,000 is also 90,625. So the congruence indeed holds. Thus we've expressed the original digits remain unchanged when squared, using the congruence. We use the fourth term as an example, but let's generalize to the nth term of p and q. Then we get this. The meaning is the same. This expresses that squaring does not change the original digits. This is one of the conditions that define p and q. There are other conditions as well. The nth term has at most n plus 1 digits, the ones digit of p is 5, and the ones digit of q is 6. Skipping intermediate steps, These conditions are known to imply the following four congruences. It almost looks like solving a quadratic equation and getting the solutions 0 and 1. But these are congruences, not equations, so I think it's better to see these as conditions rather than solutions. This also shows that the relation between P and Q resembles that between 0 and 1. It's interesting how the roles of P and Q reverse depending on whether we look at powers of 5 or powers of 2. Finally, from these congruences, the following two are also known to follow. These look very much like VOICEVOX formulas. But again, intermediate steps are skipped here. Roughly speaking, adding the previous congruences gives the first, and multiplying them gives the second. But unlike before, these focus on powers of 10 rather than powers of 2 or 5, and the reasoning that bridges them is omitted here. Now it's confirmed that these two congruences correspond to VOICEVOX formulas. First, let's check the meaning of the first congruence. It means that when the nth terms of P and Q are added and divided by 10 to the power of n plus 1, the remainder is 1. Notice anything? When the nth terms of P and Q are added and divided by 10 to the power of n plus 1, the remainder is 1. This is exactly what P plus Q equals 1 means. The second congruence works the same way. It means that when the nth terms of P and Q are multiplied and divided by 10 to the power of n plus 1, the remainder is 0. This matches the earlier PQ equals 0. So these infinite digit numbers, P and Q, satisfy something like VOICEVOX formulas. I gave a rough explanation of what's happening behind the scenes. Infinite digit calculations break down into finite digit ones, and congruences take the role of equations. How was it? If you'd like to dig deeper, please check the keywords listed in the description. Thanks for watching.
If you'd like to support this channel, consider becoming a member. In this video, we talk about the purpose of our membership. Check it out if you're interested. Well then, take care everyone.
See you later.